use those. Yeah.
Is that too bright?
I don't know.
It looked really dim, so
Let's hope there's
it up a little bit.
audio on it.
What's that?
We're using the camera audio.
All right. Do I need to push any buttons, or you got it?
Could you keep it on trained on them?
Yeah,
Just to
yeah,
go.
yeah. I can
Go. Go.
But I don't have a.
Hey everyone. Thanks for coming. Welcome to Teardown 2023. It's of course amazing to see people in person. Days turn into weeks, turn into months, turn into years, and now we're here 4 years later. For those of you who have not been to a Teardown before, welcome, and thanks for being here. Getting new people in is a big part of what we want to do. And the more people that can experience this and share their wisdom and gain your wisdom, the better. That's an ongoing process, right? Getting new people in, reaching out to new communities, and bringing them together. For those of you who have been here before, thanks for waiting and for coming again. It's really good to see people in person. At this point, I have communicated with many of you online, either email or text or those weird video fuzzy background things. But it's really nice to see everyone in person. And some of you are meeting for the first time in person, even though we've been corresponding for years. This is going to be fairly perfunctory. I've got some logistics to go over. First of all, anything that's not covered here, and I'm sure I'm not going to cover a lot, join our Discord channel. That's going to be monitored during the event, and you can ask questions, you can find out things, we'll make announcements there. The schedule, and by the way, Discord is QR codes for all of what I'm saying at the registration desk. So just take your phone out or computer, tap them, and I'll take you right there. So if you're already in Discord, join there. The schedule will be updated and the source of truth, the online schedule. So we don't have printouts anywhere here. Use your phone, use your laptop to find out the schedule. If changes are made, they'll be made there, and I'll try to remember to announce them every day. Speaking of which, every day we'll meet in this room at the beginning of the day, and then have our plenary session here, and then everyone will move over to the building next door. This is Shattuck Annex, and then the building next door across the way is all FMH, that's Fairboards Massey Hall. We're on the second floor. We get to have the entire second floor of that building. And that's where the workshops are, that's where the other talks are, that's where the demos are, installations, lounges. Speaking of lounges, we have two, actually going back to the schedule for a second. Schedule is also QR coded on the registration desk. So it'll take you right to it. You can also get to it just across Line.com with a big Teardown banner, and there's a schedule there. Lounges. Our lockpicking lounge is opening right after the plenary here, and it'll be open the entire time. Eat bag chairs, shout out to Claire and Hannah and others who have set it up. And that is the general hangout area, room 211. You'll see it on that at the registration desk, and I think also online. There's a food lounge also opposite side of the building from the registration desk, which will have snacks and catered food for breakfast and lunch. Snack time is 3:30, I think, or 3 o'clock, 3:30, I think, every day. And then tomorrow, the meals are a little bit different. We have tokens for the farmers market, Portland Farmers Market, which is right across the streets that way. Yeah, it's that big green park block. It takes up the entire park block. They're not coming to for us, we're just kind of belonging on to them. But we'll give you tokens, golden tokens that you can go spend at any vendor there for breakfast, which is 9 to 10, and for lunch, which is 1 noon to 1. And then on Sunday, we'll have food in the building. But it's a beautiful day outside, so enjoy tomorrow. It should be equally lovely. If you haven't figured out yet, Wi-Fi is PSU yes. There's no password, it is active portal. And very easy to use, seems to work great. Okay, let's see. we have a lot of the talks are being streamed online. And there'll be archived there, so if you missed one, go check it out. If you know people who wanted to be here but couldn't be, let them know. We didn't really advertise this as a mixed reality event because we're focusing on the here and now, but we hope for people to join us online. Okay, if you haven't yet registered, please do so. Right after this, go back up to the registration desk. As you know, everyone has to sign the waiver. We're here by the good graces of Oklahoma State University, which is a sponsor of the event. So thank you, Oklahoma State University College of the Arts, for allowing us to be here. Take our hand off Other two sponsors I want to thank right now are Mauser Electronics. If you don't know, Crossfly is owned by Mauser, even though we operate separately. There's at least one rep from Mauser here, so excited Joseph, if you get a chance. Mauser provided a lot of parts, as you might imagine, for some of the workshops that are happening. And the workshops, by the way, are limited, most of them are limited in the number of attendees, the number of participants, just simply because of space and materials. It'll be a first come, first serve at the time, and will help workshop coordinators look at that. Of course, to the extent possible, if you want to team up with a buddy and share a kit or something, that's totally fine. And you guys can wrestle or whatever to see if that's it. But yeah, Mauser provided a lot of those parts. Other big sponsor I wanted to mention right now is Merck Semiconductor. They'll have a demo table upstairs. A lot of the food, a lot of the resources that went into making this happen came from Nordic, so big thank you there. Their Portland team will be here as well. So thank you to Mauser and to Nordic. I'm going to hand it over to my partner, Nandini, from SETI. I'm from Proud. By the way, I'm Josh Wilson from Proud Supply. Sorry. Last things first, or first things last. So Nandini from SETI, Executive Director and Founder of SETI, take it away.
Hello, everybody. It's really lovely to see some of you again from the first time. I don't know if you remember, but we've done Teardown together about 3 times. Before my admiration was making code in another building, and SETI is our new nonprofit organization. I wanted to talk for a few minutes about SETI, just like 2 minutes. This is an art technology lab that works on lots of interesting projects, research and creative, with lots of community partners. And our lab is moving to a team. Today it's kind of like a little bit of a hurricane season. It's the staging area, so we're like doing lots of checkouts. I'm hoping we'll have it here tomorrow so we can wander through and maybe play even some tech. We're very agnostic about tech, so we do sort of hardware, software, VR, very old tech, very new tech. We have lots of tools, so come and check it out. We're open year round to everybody. And one of the things we do institute, but we really what we like to do is these messy participatory sort of communions, which Teardown is, that sort of bring a lot of people, different kinds of people together to work on technology-related, creative technology-related things. And the messy, you can see, we really want this to be the beginning of building a community. And you'll see workshops and talks, but also demos and art installations and scratch walk. And the idea is that often, like sort of learning or innovation happens accidentally when you run into somebody and have a conversation, or in sort of after parties in the evening that you don't get to know to or have already as part of your lunch box. That's when we try the farmers market. It was incredible strawberries and cherries at the moment for those who aren't prepared, especially like wine as much as you can. Oregon strawberries are special. They don't go anywhere else. They don't keep, so you have to eat them here. You only go to I recommend it. I want to mention one last thing. So we are here very around. Those of you locally come by. We do institutes in the summer and have speakers that are both local and remote that we speak, so if you're interested in those. But I want to mention one last thing about this. The goal for why we started SETI, why we do things like this, is that technology kind of permeates every part of our life. And at the moment, a very small homogeneous group gets to use the creators and power in technology. And we want to find ways and spaces to include a much broader audience who not just to consume technology, but actually feels like they can experiment with it and create with it and carry on one of those spaces. I will say that we tried, but often what happens when you try to set something up is the people you invite, people you hang out with, people who come initially, and that's all they are. We need all of you to help us find other people. So you're going to see some amazing speakers, amazing workshops, and you meet amazing people. But we'd also like you to help us decide who do you not see here that you wish to see. We want to make this really compelling gathering that happens once a year that goes community ongoing. Think about the people who should also be here. We'd love to see you. We'd love to have us tonight. We'd be really grateful for this. So we can start coming next to Teardown now. Meantime, also we want to mention, I wanted to thank all of you, just a million people, including speakers, participants, volunteers, and staff who put all of this together. And if you need help, people in the blue shirts, people who really like movies organizing, and then the people in the yellow shirts, and I have a teal scarf. There's only one of me around here, so you can give me that. I refuse to do product placement for anything, including shirts. You can find me, but we can help you find places around Portland, help you navigate around the building. The schedule has been such a wonderfully interesting work in progress that use the QR code. I don't know, but I can help you find where you need to be. But now we'll start talking on this. Josh has something to wrap, but thank you so much for coming and help us make this really amazing.
Okay, I thought about 30 things I forgot to tell you. I'll tell you all later. But without further ado, let's welcome Waylon from Square Fumi. Just a quick sec to set this up. Square Fumi launched the Watchy project on Crowd Supply a few years ago now. E-Ink, ESP32 based watch, programmable watch, big community. You're lucky because we just sold out, but we have the last 28 or so of them with the current batch. We're getting more, but there's a workshop that Waylon's running tomorrow, I believe. So take a look at that, and I'll talk to you after he tells us his gems. Okay.
I don't know if we have enough.
Hey everyone, my name is Waylon. I'm the founder of Square Fumi. It's abbreviated SQFMI. You might see this branding on our website and on our products. So today I want to share with you my journey getting into the hardware business, the mistakes I made along the way, and the lessons I learned from a novice perspective. And so hopefully this journey resonates with some of you who are along the same path. Or if you're an industry veteran, at least you'll find my mistakes entertaining, right? So let's get into it. So what do? We build open source hardware products. So every single product that we have in our store today is fully open source, PCB design files, BOM, placement, firmware, software, CAD design, mechanical docs, the website. Everything's under MIT or Creative Commons license. And what we also do as our own products is help companies go from idea to prototype and getting them ready for manufacturing. And so below you see some of the pictures of the products that we've built. There's Watchy, the BeatBerry, which is a recent product that we relaunched. And we also have Watchy with the open source hardware license that we got certified. A little bit of background about me. I did my undergrad in computer engineering. I started out building enterprise software for banks and whatnot, but I always had a passion for hardware. So sometime in my career, I transitioned to working for an IoT startup. That's when IoT was the most popular thing. And then I eventually worked at Intel working on their Maker products, on the software development tools, as well as their middleware. before I joined Meta, working under machine learning embedded framework, PyTorch. And so I've always, in my career, worked in hardware adjacent roles, right? I work with the software that powers the hardware. But I've always wanted to build my own hardware, right? So I did it on my spare time as a hobby, right? And how did that start, right? So let's go back about, a few decades. When I was a teenager, I was 17, and I was interested in two things. I was learning to play the guitar, and I was interested in robots. But when you're 17, you have no money, so you can't afford any of these things, right? So what I did was I went to the library, borrowed books, magazines, or nuts and bolts, joined like mailing lists on Yahoo, and people would share these circuit designs, right? It would be a picture, you would print it, laminate it on a copper board, and you would get something ugly like the picture at the bottom, right? This little PCB, right? And you had to borrow your friend's drill, your mom would yell at you for bringing acid into the house and things like that. And so that's how you made hardware, and it was fun, but it's also tedious, right? So imagine my surprise, fast forward, a decade or more, where you could get $5 PCBs shipped to your home, right? I had to try it out. But I didn't know anything about CAD design. So I had to learn how to do it, right? So how many of you have seen this video, Getting to Blinky, right? So this is how I got started in my journey with like learning TCAD. I designed this Blinky board with a 555 chip. And this was the first PCB hardware dev I built using CAD software. Right? And then, a week later, I get this board, right? And this was the moment that started everything. And then getting that piece of PCB with the Blinky LED was the most gratifying thing ever, right? And I've been chasing that high ever since, right? So building hardware was a lot of fun, but I didn't know anything about it. I just learned how to use a keypad. And so I went on this journey in practicing building more projects, right? I benefited a lot from the open source community by looking at designs from like Adafruit, from SparkFun, from datasheets, reference designs, just to build my own projects to learn about things, right? You can see here, I built this Lego Bluetooth controller. You can see that I didn't know what I was doing because I put the antenna right on top of a ground plate, but I was getting started, right? I was trying to bring up a mega board, with this little media controller, trying to learn how to write firmware for a keyboard, driving little LED displays, building a boost converter for like a VFD, and e-ink displays, projects, things like that. And I documented my learnings on a blog and on social media as I was going through that, right? And so just a few quick video demos of the things that I built, this little flux capacitor thing, this little robot that I tried to build using a servo controller, things like that. Right. So one of the projects that I built that eventually became my first product was Badgie, right? I found these e-ink displays that were relatively low cost at the time, and I wanted to build a board that could control it. So I stuck an ESP8266 on it, added like a LiPo and charging circuit, and I built this little project. And when you order PCBs, you always get like 5 or 10. Right? So I sold the extras on Tindy, and to my surprise, a lot of folks were interested in this product, and so I made more of them. And you can see this little demo of it. Right, just driving this e-ink display. There's my Twitter where I posted all these projects and whatnot. But as I was sharing these projects on social media and on Tindy, I got a lot of feedback for it. Right? Folks were like, well, I don't want to use pogo pins to program every time, but could you put like a USB serial converter on it, right? Could you show me some code examples of how to run this board? And so I worked on building the whole developer experience for this product, right? I showcased, how can you use WebSockets to do a canvas draw and then stream the frame buffer over to your screen. Spotify remote using the Spotify API, right? And then using the webcam API to throw the image and then sending it to Badgie. And so this inspired a lot of folks on what can you do with this product, and was a good development kit for them. A little bit of marketing using the outrun kind of imagery here, cool samples, things like that. And then we got popular on Hackaday and became the most popular product on Tindy for like about a week. And then we were sold out. And so up to this point, I was hand building some of these boards and selling them, right? And that obviously did not scale. So it was time to learn how do you go about manufacturing some of these boards. And so there's no shortage of companies out there that would take some of your money, right? You give them free files, do some magic, and you get your PCBs, right? But they do charge a premium for that, right? But it's really easy, right? You just find the right company, upload your files, and that's it. And that's what we did the first round with our badges, right? We paid some money, they did some magic, and we got a bunch of these boards back. We did the screen assembly ourselves, and then we sold a bunch of them. And then first issue with this product as we scaled up, right? We found out that the USB to serial chip that we used was not very reliable, and also there were not a lot of drivers available for like Mac OS and Linux, right? This was not a problem when we were using just one computer for development, right? As we scaled out, we realized folks had different setups, and so it was important to find a chip that supported it. But the problem is we already built a bunch of these boards, right? So what we did was we designed this tiny PCB that matched the footprint of the original chip, and we just desoldered it and placed it on top, right? And so that's the CP2104, right? It has great driver support across multiple OSs. Here's my buddy like doing the hand replacement for each of these. So that's what we did. And then, so this project became popular, and as I was saying, we kind of talked about it on social media a lot. And that's when we got notice from this developer advocate from Oracle. He's like, hey, we love this Badgie product. We're trying to do this conference thing, Oracle One. We'd like to incorporate your design, but this is the kind of mock-up you drew. And we're like, well, the skills are wrong, and we could spec a different screen for you. So we worked with them to create a whole experience, right? They wanted to demonstrate their function as a service API with this badge at the conference. So we kind of worked out the whole development workflow, the getting started, and the firmware for the board. And we're like, great, so how many of these do you want? They're like, well, we want about 5,000 or 6,000 of these, right? So I was like, great, so I guess you're not going to pay me the money, right? So I had to register for an LLC, get it set up, get onboarded as a vendor, learn about the compliance and all that. So this was the first step in setting up, Square for me as a business and working with Oracle on it. And so making 5,000 of these, as I mentioned earlier, there's a lot of vendors that will charge you a premium, give them the money to do the magic and build boards. But it was time to look for a real contract manufacturer, so to speak, right? We wanted them to load the firmware, we wanted them to test and assemble the boards, all for us, right? Because it wouldn't scale for me uploading the firmware for each single board. So we went on Alibaba, we did a search, and there was this one manufacturer that gave us a whole video tour of their manufacturing facility. And so we were really happy with what we saw. I mean, we didn't really know what we were seeing, but it looked clean, it looked professional. So we went with that, right? And then we gave us a bunch of money, and that's what happened. They sent us all these boards newly assembled and tested. We built a design jig. This was their first time understanding this was the process. You have a jig to do the programming and the testing, so we built one of those. And it was really popular. They had a great events. People were always happy to get a swag that's not just a pencil or a keychain or anything, a cool e-board to take home. And then we kept doing that, right? We worked with Google to build the NSynth, it's a machine learning synthesizer board, development kit, they worked with the Raspberry Pi. We worked with Microsoft to build this hackathon badge, and also this company in Italy that made helicopters, but they wanted an E badge. So we did a lot of conference badges, right, for these different companies. But what we really wanted to do was to build our own products, right? Not just doing manufacturing, design, and all that for other folks. And so this is where Watchy began, right? So as I was saying before, every project that I built, things as I learned, I would document it and share on social media. One of the ones was Watchy, and we realized that we hit something probably that's going to be a hit because we saw a lot of retweets, a lot of likes, a lot of comments, a lot of feedback. So we wanted to pursue that idea. So here's a quick demo of it with the old school Nintendo Game & Watch, right? Showing the octopus. Right? And so the first iteration, I was still learning a lot about building hardware. We made this prototype with an ESP module. It was dual-sided assembly. It made it really thick. A lot of things weren't optimized, but it gave us a platform to develop the firmware, to test it, and showcase the idea and potential of this product. And then, we optimized it, made it a single-layer assembly. We got the ESP chip instead of using the module, so we reduced the thickness by a lot. So it was more watch-like at this point. And we made a bunch of these. I think we made around 400 or 500 of these to sell on TVs. So at that point, we showcased some code examples, some documentation on what it is, what it looks like. You'll see the HTML bomb plugin for KiCad here, showcasing what the thing does. Explosion view of the product. And it was a great success because we sold Watchies and we shipped them around the world. We have Watchies on every continent except for Antarctica, right? Alaska, Hawaii, Asia, Africa. And we get all this interesting projects that people built using the Watchie platform. And that's when we went viral, right? We built 500 of these, we shipped them all out, but then we got the media to notice us, right? The Verge, Gizmodo, IEEE, people were always talking about Washi, like tweeting about it, but we had a problem because we were sold out at this point, right? And so it caught us into that time, and when we checked our Tindy store, we had 8,000 people on the wait list, right? So what did we do, right? Like, I didn't have the capital, and I didn't want to risk my capital making 8,000 of these and end up, people not wanting to buy them in the end, right? So we went with Crowd Supply to crowdfund this whole project. It was great because they provided us with resources like, here's some vetted vendors you can work with, logistics about packaging, shipping. And so with all that, we got our funding. So now we have to deliver the product, right? How do we deliver this product? Well, first issue is that this was 2021 when we launched, so supply chain issues, right? How many of you in the audience have had supply chain issues in the past 2 years, right? The products are building, pretty much everyone, right? So the most critical piece, right? You can't build a watch without a clock, right? So the RTC chip that we were using went from 60 cents to $3 to $11 per piece to, we can't even source it at all. So we quickly had to change our design, right? We're lucky that we tried to source these parts before we actually made all the PCBs, right? So we quickly iterated and changed the design to another chip, which was very small in footprint, so it fit in the same proximate area. It didn't have the nice temperature compensation and the built-in oscillator, but it was a compromise that we had to make for every movement. And right as I was about to make this change in design, we saw the price go up for this chip as well. So when I found out there was a warehouse in Germany from Aero that had like 6,000 of these, right? Just whipped up my credit card and just bought all of them, right? So I could have stock for it. The CP2114, the USB serial chip that I mentioned earlier, that also went up in price as well. So that definitely affected our margin, but there wasn't a good replacement for that at the time. And then when you make many thousands of something, you run into issues that you didn't see when you're making 100, right? The buttons that we originally sourced, they were not of the highest qualities, but plastic became brittle after reflowing. And so what we did is we changed the brand to the Panasonic brand, and we didn't have those issues afterwards, right? The buttons kept breaking when we were reflowing. We had to create a comprehensive test plan because every watchie that you ship that doesn't work, right, you have to get a return. And once you assemble it, there's no easy way to repair it. So we want to minimize this to occur and improve our yield. So we put together this testing firmware. We would test the RTC, the screen, and everything, and we shared this with the documentation with our manufacturer to get this done. And then when we launched the campaign, we got a lot of feedback from our backers. They're like, does it come with an enclosure? Like, I don't want a bare PCB on my wrist, right? Can I use a different mousetrap? strap? And we got this funding, and there's so much potential that we could do with this product. So why don't we, build a case for it? Why not? But the problem was I didn't know anything about CAD design either, right? So I went to YouTube right away, learn Fusion fast, right? How do you learn Fusion 360, right, in 5 minutes? And so you see all these ugly prototypes that I built and printed with my 3D printer as I was trying to learn how to use this CAD tool, experimenting with different designs. And then as I was doing this, I shared all of these on social media, getting feedback from folks like, hey, this is really ugly, this is really nice, could you make this one and whatnot? And then we improved on the design, and we let Twitter vote on the design they wanted for the enclosure. In the end, we chose the one in the middle for the CNC metal enclosure, which you could buy as an option. And we included the injection molded case, the black one at the bottom on the left. But we also had another issue, right? But first of all, let's go through this. So, with the CNC case, it was pretty straightforward. We designed it, shared the step files with the manufacturer, and they gave us these really nice anodized aluminum case for watching. The buttons work great, they look great, and we're selling them. Injection molding was the tricky part because we knew nothing about injection molding. For this case, we didn't use any screws to keep the two pieces together. They were snap-ons. So designing a flexible and moldable case two-piece design was a challenge. We knew nothing about injection molding. So off to YouTube again, learning about draft angles, injection molding. And here's a video of the mold being made by our manufacturer. This is it's one piece, right? And it covers the top and bottom side of the mold along with the buttons. And the cool thing with the injection molding is you can switch out the plastic, and so we also made this clear case. which is this cool visual look on it. And so a lot of times when we get these hardware kits, it's an anti-static bag with a brown box, right? And that's not very fun and interesting. So we wanted to do something that's more fun. We designed this flat pack packaging where it's exciting to get out of the box, right? Once you slide it open, you see all the parts at first glance. We went with this IKEA style, assembly instructions just to kind of give folks an idea of how to put it together. And then we also shared this documentation with our manufacturer how to properly put the pieces into the packaging, right? And so we always have that when you ship over to Product Supply and Housing over to our backers. Documentation is super important for products like these, teaching folks how to get started, the right way to assemble it. And then we started a Discord community, right? So we got about 3,000 active users now, right? So it's great for folks to share their own designs, to kind of help each other out on commonly asked questions. Some folks developed a simulator for watching. And on the far corner, you see all the different watch face designs built by the community. And so we had another thought in our head, right? So after we delivered to all our backers, we had our newfound experience of manufacturing with a contract manufacturer. Well, why not manufacture watching in-house, right? How hard could it be to work a P&D machine, right? So there's a talk there today. I'm sure you guys will be really interested to learn how hard it is to work a pick-and-place machine. So we're super excited. We bought this machine. It's a small, medium-sized machine. Right? We set it up, bought a reflow oven, and then I'll play all these videos of us trying to get this working, right? So you notice how hard it's pressing against the PCB, right? So we had to adjust the angle, right? It's pushing way too hard. We have to reinforce it. And if you look at the far right picture there, that's all the rejected parts shown in the placement, right? So imagine setting up a regular 2D printer, right? Then tuning a 3D printer, and then setting up a pick-and-place machine. That's the level of complexity and pain and frustration I would rate it. But eventually, we learned a lot about the machine, and we got it working. And so then we started building watches in-house, right? So here are all the PCBs that we placed and reflowed, tested, and packaged. And now we're making these ourselves. And so 1 year review, we shipped thousands of units globally. We have distributors for this product in 5 countries, about 3,000 users on Discord and also GitHub. A lot of PRs and features on different aspects of watching, different watch faces, as well as different improvements. We improved the battery life from 7 days to 3 weeks now. And I picked up a few interesting use cases here. Right? Someone used their watchie as an Escape speed monitor controller. We got this cool Donkey Kong watch face. Someone ported over the original Tamagotchi ROM to watchie. And someone hacked NFC payments over to watchie as well. And then on social media, one day, a prop master from Sony Studios reached out to us and said, hey, we really love the idea of watchie. We'd like to feature it in our upcoming season of For All Mankind. And so this is super exciting for us, right? So they wanted a customized watch face and enclosure for their show. And so watchie became the official watch for the Helios Space Crew for All Mankind Season 3. You guys watch the show. And so this is kind of how I felt after my journey, right? I collected all the gems of like software, firmware, business marketing, industrial, all that, right? But of course, at a very, novice, beginner level. But I feel like going through this journey where you need to kind of have a bit of everything to pull together a project like that and have success with it. And so what's next, right? So right now we're working on the Beeper product, which is a Raspberry Pi powered pocket computer thing. You see it running Doom on the monochrome LCD display. We're also building a portable air quality monitor. And this is the first time we're seeing watchie 2, right, which is something that will launch in the near future. And so that's it. Thank you.
Okay, thank you. Any questions? I have some, but yeah, let me come over to you.
This one's not so much about the tech, but about the process. When you started talking, it was one about I did this and I did that, and about halfway through the talk, it was we. Can you talk a little bit about how, like, is it a company? Did it grow? Do you have employees? Are you like man on the job still, and you just like to talk kind of in the third person?
So we got this. Hang on.
Sorry. So I'm talking in third person, just inclusive of all the folks that we work with, but I'm the, I guess, only full-time person that's working at this company. We do hire some contractors, but mostly just friends of mine. For example, the buddy you saw in the picture earlier, just helping out here and there. For the manufacturing of PCBs and all of that's obviously outsourced, right? Running the PCBA is myself and also some friends that are around to help out. But we don't have any kind of full-time or even part-time employees. It's kind of a one-man kind of part-time business right now. So,
Okay.
So thanks for that, really. I've sort of been through that adventure too. The two things. Are you past the pit of despair? Do you know what that is? That's one. And two, did you notice, was there any benefits for starting to manufacture in-house? In other words, sometimes you look at the numbers and you say, if you use a CM, this is their cost. And if you bring it in, this is your cost. But now you've got the machine, you've got the space, you've got the electricity, and all these things. And I wonder if you feel that's a fair trade-off to have made.
So the quick and simple answer is no, it's not worth it. Right? So part of the reason you said that when we ventured into doing the PCB design, doing the injection molding, consistency, all this is like, what if and why not, right? That was the same motivation of doing the manufacturing in-house. It's like, what is it like, right? It's kind of like the tinker hacker in mindset where you want to try doing it yourselves. It has not become like, if I went with the CM to get us made, we would reduce the cost. Not significantly by enough to make it not worth the trouble for doing this, right? But it's part of the learning process as well. And getting that close to it helped us better understand how the manufacturers go through this process, even though the machinery and the process is slightly different. But that gives me a better understanding of how the sausage is made, so to speak. So then that gives me some empathy and understanding of what I need to do better in terms of designing for manufacturing. So, yeah. But monetary-wise, it's not worth it, for sure.
So I'm just curious, what kind of compliance issues you had to work through? Did you have to do like RF testing or get any other certifications or things like that?
With our own manufacturing setup, we're still going through that process of getting that certified. So we're not sure if we'll go all the way because we might end up just using the CMD and it's a good exercise to practice. So, but yeah, those are the three main things there. We have to go through in compliance.
I had a question for you, and I'll get other people in a sec. There's a slide where you were explaining what you did about two parts that were short in supply. One of them you replaced with the entire PCB. The other one you said, well, it became more
how is the programming done? Is it all done through the USB port, or done through Wi-Fi, or what mechanism do you actually customize?
It's done through a USB serial, so it uses the ESP IDF toolchain, so the firmware just gets loaded over USB. You can also upload it over Wi-Fi as well, so it's kind of like an OTA upload, but mainly it's through the USB serial connection.
When you got to the part about the documentation, I got really excited with your diagrams and your IKEA style like renderings and stuff. Is that an area you geeked out on, or do you have a lot of help with? Because I'd love to hear a whole presentation on that.
So I think this is a great opportunity to give a shout out to all the graphic designers and artists out there. I've worked with a very talented graphic designer that we just kind of have the synergy point. He understands exactly my vision of what I'm trying to create. And so all the beautiful documentation that you see on the website, the diagrams, I work with him to kind of create. So definitely, if this is not a skill set you already possess, work with someone, maybe someone here today that you can partner with to kind of build that out. So.
Getting my steps in. There you go.
Thank you. I feel like this is a bit of a cheap question that you've already slightly answered, but is there anything you would have done differently? Anything you would have started earlier or not done at all or done instead?
Yeah, I think the biggest difference is just the gap in knowledge that I had when I first started this about manufacturing electronics in general, and the slightly more knowledge that I have now, but still there's a lot of unknowns for it. So things like how to properly panelize these boards, how do you kind of design to make placement less error prone, where are the most common manufacturing errors for it. How do you kind of more efficiently develop this assembly process guide and communicate that with your manufacturer, right? Because they don't know what your product does. They just have this source of files, right, that they are supposed to build. So really kind of like laying that out carefully, that reduces a lot of frustration and time wasted and back and forth, right? So I think that's the experience that I gained, and I think next time I have to do a similar project like this, that's what I would do differently, and hopefully save a lot of time on paying from that.
Great talk, thanks. Where are you located, and how do you feel about using community spaces versus building out like limited urban space? I don't know.
So I'm based out of New York City. We have a few machines in my tiny apartment. That's the only place that I would fit. I think community spaces is maybe not so applicable to in terms of like PCBA and that type of. It's not as common as I see it today. Right? A lot of community spaces you see, power tools, 3D printed machines, laser cutters. There's less places where you see like pick and place machines and like into electronics, right? So maybe that will change in the future, but right now I would say for electronics type of setups, I haven't seen a lot of community places where you take advantage of that to use the space.
Hi there. A question about CNC versus injection molding. I know that the cost of injection molding, the mold it's too high, CNC is less, but per unit it's more. So any advice on that, when to go with CNC, when to go with injection molding, that would be great.
I think the decision should come from whether your product looks better or fits more with a metal type of closure or plastic, right? With us, obviously, injection molding only makes sense when we're making thousands and thousands of these units from a cost perspective. But we did find out that there's actually lower cost injection molding as well. Sometimes they can make the molds even out of aluminum, right? But they don't last as long. So depending on the precision of the pieces they're making, maybe it makes sense to just sort of a low cost, injection molding. Maybe it can be silicon as well, so those are even cheaper. But I think it depends on what kind of product you're trying to make, right? With the CNC one, we obviously sold it as an upgrade, so there was profit to be made by selling that, so that made sense for us to use premium materials. Injection molding made it more cost effective for us to just include a case for every single kit because we're making so many of them. So I would say it depends on the look and feel you want really for your product, less so on from a cost perspective.
Hi, so have you been bitten by having an open source license, and do you plan to have your future products be fully open source like this one's?
So being bitten by open source license, are you referring to just compliance in general, or just like people taking your design, or what's the
downside?
The downsides of it. So I don't see, okay, one interesting story, I don't see it necessarily as a downside. So if you go on AliExpress today, you will see a clone of Washi, right? There's someone that's making something, obviously from our open source design files, they made it only slightly cheaper. But I think that's okay because that really proves that this becomes a successful product. People want to copy and clone it. Because we benefited so much from the open source community, we really want to give back and just keep this open source ethos. And we also benefit from it as well because, especially with a developer type of product, we want the developers to be enabled by tinkering with it, understanding how it works so they can make the most with it. Maybe if you're making a more consumer-oriented product, the open sourcing has less value to the consumer because, well, I'm not going to open it up or I don't really care how it works, right? It just needs to work. So for our type of products, I believe open source has been more beneficial than not.
And future products?
Future products, yes. I think we'll continue down the path with building a more developer kit type of hacker maker type of products. So we'll continue with this open sourcing.
Hi. At one point in your presentation, you said you made the jump from standard like PCB all PCB. You went from them to a contract manufacturer that you've sought out on AliExpress. What did you find was the biggest benefit, and what was the difference in your workflow or experience by making that change?
To kind of simplify it, I would say when working with companies like PCBWay, it's like they're holding your hand along the way, almost in a way where like they built a lot of these projects for the Western world, right? They're English speakers, so it's very straightforward, right? They understand what you're trying to build, and they'll help you even if you have design issues. They'll help you correctly. With these other country manufacturers, the biggest benefit is cost, right? They're usually cheaper and lower cost in terms of assembly per piece, but you have to be very specific about the instructions of what you're trying to do, what you're trying to build. Have everything really well documented, so they're able to follow along because they probably don't have as much context as what you're trying to build, and sometimes they don't have as strong as a relationship with the supply chain. So asking them to source something, you might have to do it yourself rather than I'll figure out what the parts where they are and I can buy for you. But if you source it yourself, the benefit is you can get a lower cost as well. So that's the biggest difference, I would say.
Right. So there are a lot of projects that I might do, but I don't feel so comfortable working with like very small packages. Everybody has their personal comfort level with SMD parts or things like that. So I guess when you were miniaturizing the Wachi, you probably ran into some point in which you may not feel comfortable with trying to prototype yourself. And I know you have a pick and place machine now, but so how do you sort of overcome that point in the manufacturing process where you're not really comfortable or able to really do this work at quantity 1, quantity 5 level?
I think it depends on the products and what level of miniaturization you need to get to. So for example, with Wachi, the smallest component we have are 0402s. And so even when we prototyped it, I kind of hand placed some of those, right? They didn't always work, but you could just fiddle around with it to get it working. And I think most manufacturers are fine with that, even down to 0201. There shouldn't be issues if they're a professional, contract manufacturer. They should be able to handle that. If you're seeing some yield issues, right, with your design and surplacing it, you might get some feedback from them on how to better design and lay it out so that you're not running into it. But I don't think even down to that size, usually it's an issue with the manufacturer. It might be harder for you to validate that design to hand place it, right? But maybe it's just a matter of, spending some upfront costs to get them to build you, let's say, 10 prototypes or using their professional machine and validating that. I think for Washi, there's even not much more that we need to miniaturize, given that the screen is something that you can't make any smaller, so any space behind it we can use. So I think that's 042 is kind of the middle of the right now.
One more question. I think that there's kind of this interesting question of when the NREs cross over. And so I think that was kind of alluded to in terms of injection molding NREs, but I feel like there's a lot of NREs at quantity 5,000 or quantity 6,000. And I sort of feel like my intuition to this is that all of your margin goes away instantly and you break even, but you don't pay rent anymore. So I'm curious where you found that, where you found the NRE crossover, and how you balanced it with being a full-time sort of thing.
So when we did the injection molding for the Washi product, one of the things that we were hoping for was just to kind of at least break even, because it was kind of just like, let's try it out and see what it's like to do an injection mold, right? I think even at the quantity that we were doing it at, it wasn't really a very profitable situation because the molds, the upfront cost is significant, right, compared to the other manufacturing techniques. And so, but we really wanted to try it out. What is it like to make a plastic injection molding case, right? So I think if you're applying this a bit more ahead where you're thinking like, I need to be profitable in terms of like my entire bomb, getting a mold made for it, you need to be looking at significant quantity for it before it starts to make sense, right? And I think there are other techniques that you can look at today, like even 3D printing at a lot of shops is very reasonably priced at small scale. So I think that's a great alternative these days if you're just trying to make like a couple hundred or something, right? But you can always make your product more expensive to accommodate for it, right? So kind of think about it in terms of not necessarily just like bomb times 3, but the value that you're providing for the product, right? And if you can create tremendous value, like like an iPhone, then you can be multiple X of the cost of your bomb to deliver a product. So I think that's a way that I would look at designing the manufacturing process and the end product look and feel that you want to go for.
Great. I'm going to hold any other questions. If you have other questions, and I have some, we actually have a breakout session. I think it's on Sunday. I believe you're going to be there. Yep, great. The breakout session is called something to the effect of building a business out of open source hardware. And it will be a real conversation. It's not as one speaker, but there'll be a few people just kind of giving an introduction, and then anybody who wants to chat about it and share their thoughts or questions, would be welcome to. We have 2 other breakout sessions, so one each day. That's the Sunday breakout session. We have a breakout session today about, I believe it is the exotic PCBs and how do you get access to them, so the exotic PCB manufacturing processes. Bunny, I think, is back there. We'll give the intro there. And then tomorrow we have the Open Silicon breakout session. We have a few talks about that. Unfortunately, one of them couldn't make it today. He wasn't feeling well and did his public health duty and told us and is staying away. Speaking of which, if you're not feeling well, please don't make other people not feel well also. We have immunocompromised folks among us, and we're still being careful. The buildings that we're in have great HVAC systems. There are air purifiers there as well, or air filters. So we're confident in the safety, but also we're going to rely on your good judgment to keep us safe. You had a great plug for Fusion 360, which is awesome, because they are a sponsor also. Autodesk has a headquarters here. We're going to go there tonight. So the after hours event, one of them is at Autodesk. So the things here end at 6 o'clock. You'll make your own way over to Autodesk. It's across the river. It's not very far. You could walk it. You could take the bus. We'll put things in Discord about how to get there exactly if you want to do that. And they're hosting us for dinner and fun tonight. Tomorrow night will be Control H, our permanent local hackerspace. We'll give you directions there. It's on the schedule as well. And then Sunday night, we're heading up toward Craft Supply headquarters and some of our favorite hangouts in North Portland. Thank you again for coming. Let's give a big round of applause to Ellen. I'm looking forward to a great weekend with you all. Thanks. We're all going to exit this room here. If you have any questions, you can ask anyone in a yellow version of this shirt, as you can see someone back there is wearing. We're going back up to the second floor of FMH, which is right across the way.
Let's see if we can make this. Give it a second.
Guarantees there.
What is making the? There, that's working.
Right.
Yep. It's coming through. Yes.
Call it good. Tomorrow we'll simplify.
Yeah. They asked him when he's ready if he wants to do the function, but we should have started Okay.
I think we're ready. In the interest of time, I'm going to forego the usual kind of introduction. Go ahead and introduce myself. I'm Professor David Burdett, and I'm faculty in electrical and computer engineering here at Portland State University. This is millimeter modes, where I make a case for getting rid of PCBs forever. I have this goal to get rid of them. I can't stand having this dummy chunk of fiberglass in every electronic assembly that's doing nothing but providing routing and mechanical stability. We need to be able to get rid of it, but first we need to come up with some interesting circuit design level insights that let us get rid of all the stuff we usually assemble in PCBs. I run what I call a WEST lab, a wireless environmental sensor technology lab. I have a lot of examples of environmental sensors, wireless environmental sensors that we have made and could make in the future later on, especially stuff that we can create uniquely with stuff that is designed exclusively in silicon. First off, I want to talk about a little bit about how I got here, because my pre-PhD career is all big stuff with lots of PCBs. I have a couple examples there. I need to introduce the concept of wireless modules in contrast to wireless SoC systems on chip, the actual chip that you would buy that does RF communication versus a complete system, and how we're kind of comparing these things. Talk about on-chip frequency generation, my favorite research topic. Folks fall thicker in that section. I won't be offended. I understand it's quite dry. It's one of those pivotal, almost mathematical sorts of insights that you need in order to figure out how to get rid of all the stuff that would go on PCB, and then I'll talk about my hopes and dreams for my research career if folks like the National Science Foundation want to write me a check for several $million. If anyone out there has that amount of money and wants to support this sort of research, I'm all here. So how did I get here? Well, one of my first projects back in college was a long-range bioacoustic system of the University of Washington. This with one of our team members standing here for scale. This would send out a loud acoustic ping, a chirp between 8 and 12 kilohertz. It would travel at something like 2 to 5 kilometers, depending on ocean state. Reflect off of fish pods, off of the air-filled swim bladders. We get an acoustic response and figure out how many fish are out there without having to go out and tow a net and pick up the fish and pump them. Well, we did that for around 3 days. Huge device, horrendously power hungry. One of these two big metal cylinders is a PC-104 stack Linux computer that I was the administrator of. The other stack are all mixed signal, digital analog converters and ADCs to do all of the analog interface. Just a horrendous amount of effort. That was really fun though, and got me started on another set of projects back when I was a member of technical staff at Sandy National Labs. We were designing intertidal intruder detection systems. On land, it's kind of easy to build a fence that works pretty well. In deep water, it's, well, I don't want to say easy, but it's fairly well understood on how to use acoustics to see someone swimming in that intertidal section that's sometimes flooded and sometimes not. All bets are off. And so we were coming up with zillions of ways and testing all over the country. Also super exciting, big engineering, lots of PCBs involved in all that stuff. And then my third big project was this underwater robot that was all custom design involving freezing your face off down in Remoto Station. And I've got a picture over here in the corner was taken at 3 in the morning with the team members. Also, right, big underwater, heavy duty stuff. Of course, what did I do when I went to grad school? I thought, how much bigger are devices getting in the future, right? What is the future? What is the research edge of electrical engineering? And it's not big stuff, in my opinion. It was small stuff. So one of my first projects at the very beginning was the circadian state estimator with a postdoc out of the School of Psychology. You're now kind of broaching, it's about 10 years ago, broaching on the subject of wearables. This is when Fitbit stuff was just starting to hit the market, and we were trying to come up with other clever ways of inferring, doing kind of health measurements and figuring out what's going on in the body through non-invasive wearable things at the time. Sleep studies, sleep wearable devices were these giant backpacks that included a rectal thermometer, not exactly something that is going to effectively let you live your life while it's monitoring. It's totally upsetting. In a lot of these sleep studies, women stop ovulating. You just completely mess up the experiment by having these things. So we were trying to figure out how to have smaller, unobtrusive things. We had a couple of generations. Now these same sorts of pieces of technology are integrated. These little ring doodads, but this was one of the beginnings. So this was all going, okay, I built a lot of really big things, and I felt like I was designing essentially the same embedded system over and over and over again to fit into a gigantic machine. But if I wanted to do PhD research, I wanted to figure out what was the new stuff, what was coming out of the pipe. And for me, that was biomedical, it's implantable, it's tiny, tiny little chips. And so I was like, I need to get into integrated circuits. That's why I started out. So to talk about the innovations that we figured out back during my PhD and that I'm carrying forward here at PSU in the millimeter scale environmental sensors as opposed to meter scale or more environmental sensors. We need to briefly introduce the concept of a wireless module as compared to a wireless SoC. A module is a complete communication system. We got 3 examples from academia and 3 examples from industry displayed up here. And since something like 2011, right, the Silas Blue Gate was one of the first Bluetooth low energy modules to come out. They're all kind of a centimeter on the side. And this is still true to this day. If you want to design something that is a complete device that is a standalone object that does wireless communication, you pair this with a battery of appropriate size, depending on whatever your longevity needs are. You're going to end up with this black plastic rectangle in the middle, maybe one of these metal shields on top in order to get FCC certification. And you're going to need all of these off-chip components that are mandatory to support the SoC. What we ended up doing, and what was secretly pictured on the previous slide, is switching all this stuff into a single IC. We were able to integrate or eliminate all of the off-chip components that you usually need. SAM's antenna, that's one sort of asterisk to a lot of this. If I go back 1 slide, or 2 slides, I pictured the chip to scale up here in the corner. So my dream is to get one of these implanted under my skin someday. As soon as I can figure out how to power it for long enough, then I'll be off to the races. So we ended up, so this is also to scale, right? We've got a couple tens of millimeters, and we got this down to just a couple of millimeters on the side. There's no reason why we can't continue to reduce that with smaller and smaller transistor processors. So why have we been, and how we actually to this day, kind of stuck at this approximately 1 centimeter scale? And that's because all this stuff that you need in order to support what I've labeled here the main radio / processor IC. You've got lots of passives, you've got some terminals. If you want to actually plug something in, you've got to have probably 0.1 inch spacing headers. You've got some sensors, power regulation, and most importantly, these red boxes are the crystals. Most designs require or recommend 2, all of them require at least 1. And the big key innovation that we figured out is that you can do without that crystal oscillator. You can cut it, design a clever circuit to provide feedback and calibration, through an alternative method. And if you can eliminate those two things, well, the rest of these are a little more easy to integrate, and you end up with something that is just a piece of silicon on top of what I've got pictured here, the smallest, easily accessible off-the-shelf battery, the 337 silver oxide battery. So that's the big thing, and there has been a lot of work done in eliminating the crystal oscillator and having so-called free-running oscillators that are just, you power them up, they start at sort of whatever frequency, and away you go. The thing we were able to figure out is you can still do standards compatible interoperability with commercial stuff. So this chip, if we optically program it, attach it to a power source, it'll start blasting Bluetooth packets that all our phones can hear, as opposed to having something that starts up at who knows what frequency, and it's not going to be communicating at a recognized standard that is going to be interoperable with the billions of devices we already have. So this is the device. We're kind of quick, especially in the a little too many slide advances. So it is, if you just look at the list of capabilities off here on one side, it's effectively a wireless microcontroller. It's got an ARM Cortex-M0, it's running blazing fast, 20 megahertz. We usually run it at 5, but we don't need a whole lot of horsepower. In fact, we don't want it for the size scale that we're going after. We don't want to be consuming a lot of power, so we clock the CPU way down. A teeny amount, but just enough. Programming data memory, 64K of each. And we need 3 wires. We need battery plus and minus, we need some power source, and some antenna. It turns out an antenna is just a piece of wire, and a good antenna is a piece of wire of appropriate size. So a bad antenna you can fit on top of the chip. We have to just drill a wire bond across the end of the chip. You want to do something like a 20 dB hit to your link margin, but you can still have your phone across the room. It's not catastrophically bad.
So you have to use the bond wire as an antenna?
Yeah, we use the bond wire as an antenna. We drew it from, I think this is the antenna thing right here, and found the capacitive input somewhere at the other end is through this whole arc. As I mentioned earlier, it performs badly, but it doesn't perform, not at all. That's the important.
It's still pretty neat.
If we attach a proper antenna to it, we have many meters of range. But we get something like 1 meter of range with a bond wire. And that's at 2.4 gigahertz, so we're sort of shooting ourselves in the foot by choosing a wavelength that is much longer than the largest dimension of the chip. If we switch to 24 gigahertz or 60 gigahertz, that's actually well-published information. There are on-chip antennas that have demonstrated they work really well. But speaking 2.4 gigahertz was really important from an interoperability standpoint. We all carry zillions of devices that will interact with them. And then also, go ahead. Yeah, please.
Did you say they could do 60 gigahertz or 60 megahertz?
I'm saying if you redesigned a 60 gigahertz, you could fit a resonant antenna on chip.
Okay.
As it stands, you have both fitting resonant antenna right here. 12.5 centimeters is much larger than 2 millimeters. So
It's got a pretty scale attached to the wire.
Yeah. And one important bullet here is that this runs the IETF standardized OpenWSN wireless mesh networking system that came out of my lab, my PhD lab years prior. So this can join an IP network. Each one of these little devices can have an IP6 address and be addressable from out in the world. There's no technical limit to how many devices can be part of a mesh network like this. The commercial implementation says, well, if you're using our proprietary devices, probably call us if you're going to go through more than 50,000. But there are there's no it's a RAM limit basically of a host computer in terms of how many entries it can reasonably have. So anyway, we can power this from a whole bunch of other things, solar arrays, printed batteries, and this is the 65 nanometer CMOS, which for those of you who know, that's big. We redesigned this in 5 nanometer. We can shrink this down. We have redesigned in 28 nanometer. That was a class that I created about 5 or 6 years ago that just redesigned all these pieces.
Am I hearing that you have some sort of fab here?
Or where's this from?
Yeah, thankfully, we're not trying to fab a couple million or more transistors on our own. This is through TSMC. So the 61 nanometer process was provided through TSMC. 28 nanometer, that redesign for the course was through ST Micro. And as you know, there are several options in terms of fab. It's really just sort of which process are you most familiar with and which process do you for. Yeah.
How, you showed the size of it for the dimensions, but how thick is it? Like, is it the same kind of size as a chip that you'd be like on an RFID charter?
When we order it, backlap it down to 0.3 millimeters.
Okay. And is it single layers or multi?
It is, well, I guess it depends on what you mean by single layer and multi. There's a single layer of transistors, and then there's about 10 metal routing layers on top.
Okay.
With an ultra thick metal layer up at the very top in order to get decent conductor capabilities. Not great, but okay. Certainly great for one chip, but not great compared to an optic activity. All right, so what do you do with this? Well, my favorite one is that you glue it to beads and follow them. There's this problem with invasive insects coming down just across the border. Canada, the Griffin Iyer at UW was involved in his own efforts to instrument beads, but we had some friends over at Emory in Paris who were faced with the same problem. And so we shipped the folks, the sort of grad students who came after me, assembled a little kit, complete with battery, conductive tape, programmer, the chips, and said, you get out of the field, you open the case, follow instructions, glue it to one of these invasive species, and hopefully we can find it. The biggest thing we learned from this is that beeswax is actually much better adhesive than what we were trying to do. So weirdly enough, beeswax sticks to hornets really well. So the next time is we try this, hopefully soon, now that my lab here has produced a new generation of fuselages to power these things, hopefully we'll get another shot. So one of the things I want to point out is that through this development, you can compress your entire design into a single chunk of silicon instead of having a bunch of object components. We can do this thing that I call we have new tiers of capability. The three things that we're trying to improve are lifetime size, and cost. And we can all already think of designs that are much better in one of these at the cost of the other two. Maybe we use kind of two at once. And for optimizing two instead of at the cost of the third, there are some examples, but we can't do all three at once. We can't make a really long-lived, in other words, low power, ultra small, super integrated, and probably inexpensive at scale. We mass produce these things. We're using giant 12-inch wafer fabs that could churn out millions of these things all at once. We could drive the cost down by kind of a stupendous amount. This 25-cent number here is not made up. That's a fairly reasonable thing. If we can do just one really well, we have all sorts of fun applications. But if we do all three, we now can finally do things insects and so on and so forth. And I want to note, this is one of the most kind of surprising footnotes whenever I think about this stuff, is that improving in one also can improve the other. For example, if you make a physically smaller chip, if you reduce the form factor of this thing even more, you do reduce the cost per chip because you get more squares chopped out of a 12-inch circle than you would otherwise. So if you can save a little bit in silicon, your per unit cost goes down. Potentially, a lower power, if you're able to redesign the circuits and reduce the active power rate, or certainly the sleep power, you shrink the battery, and the battery is most of the design at this point. The battery is most of the design. That makes me really happy because I think besides PCBs being fully eradicated and doing design entirely in silicon, I think these wireless sensor things should be more like rockets. And that is, they should be mostly fuel. And if you need to go, if you need less distance or you need to boost less payload, you just have a smaller thing and burn less fuel. Our single chip mode IC, 4.2 milligrams, is pictured here with the smallest easily obtainable button cell battery. But if you want the thing to last twice as long, you just get a battery that's twice as big. And so now your form factor and your mass scale directly with lifetime and application, as opposed to for these really cut down, low power, environmental sensor devices. Right now it's mostly a Pelican case. And if there's some battery in there, that's fine, but the volume is this giant box. We want to do away with the box and the PCB and all the opposite components, and we just some silicon, the thing that's actually doing the work, the silicon, and it's really only the top 10% of the silicon. The rest is dead, so we can shave that even further down and cut more of these nodes off. And all that's left is the thing that's providing it. That's the goal, and that's something that we're able to enable. A little aside on frequencies, things are somewhat light start. I'm going to try to rapidly run through this. If you have a crystal, this crystal here is part of this phase lock loop, you have one of those, you have the ability to constrain frequency error and to calibrate a VCO, voltage controlled oscillator. And you have something that on chip is running at 2.40000 gigahertz, and it starts to wander because the temperature change, random fluctuation, that crystal is going to provide a signal that goes, no, you're running a little too fast, you're running a little too slow, and it provides this correction. And so you end up with a ceiling of error up here at the loop time constant at the speed at which the PLL is able to run. You cut those out here in the second figure. All you've got is a free running local oscillator, and so as it accumulates error, there's nothing to fix it. That's something you don't necessarily want. It's really important to have an accurate sense of time when you're doing wireless communication, because wireless communication at the end of the day is something we've all just agreed on, something we agreed upon. It's a specification, it's a standard that we've all kind of sat in a room and argued usually for about 10 years to get one of these standards ratified. And we all agree that, okay, in this frequency band, dividing that frequency band into these little slices we call channels. Inside of each channel, we are going to modulate our frequency at a certain rate in order to represent data. That modulation rate is going to consume a certain amount of bandwidth. We're all agreed that this is how it's going to work. And so for frequency shifting, it's one of a zillion different ways to modulate that RF signal. We need at least 4 senses of time. We need to agree on what the center frequency is. We need to agree about on how far we're going to adjust the center frequency to represent a 1 or 0. We're going to adjust it a little high and a little low to represent a 1 or 0. These examples are up here all for Bluetooth low energy. We need to agree how often we're going to shift that frequency to represent the data rate. So 1 megabit per second means that every microsecond we may or may not change the frequency of the oscillator. And then really important for some of these deeply duty cycle low power systems, we need to all agree on what time we'll wake up, exchange information, and go back. These radios consume the vast majority of the active power in any system. And so we want to have them off all the time, except for at the very last moment, you want to be able to go, okay, it's time, we're going to turn on the receiver. I know a package is going to show up soon. There's always going to be a little bit of error in that estimate, so you wake up a little early every time until dark time. But you generally need a fairly accurate timer in order to schedule that. This, I'm mentioning these statistics here because I'm going to throw a lot of plots at you. There's going to be a red line at 20, below is good, above is bad. So my favorite standards are Bluetooth low energy, and IEEE 15.4. 15.4, most people have not heard of, but they have heard of Zigbee, which is the physical layer that Zigbee is. This is the physical layer Zigbee is built on top of. So it follows 15.4, and then they build their own network stack on top of it. And it's a really popular physical layer specification. A lot of IoT stuff ends up, you dig down far enough, you find out it's data 15.4. So 20 to 50 ppm, depending on which thing we're talking about. Parts per million, if you're not familiar with parts per million, it's 4 more zeros instead of 1%. Now, 1% is sort of 1 part per 100. You add 4 zeros, now you've got 1 part per million. It's a really narrow specification. All right, we don't have to talk about this much, but I do need to mention that the plots that are going to come up soon are Allen variance or Allen deviation plots. The big thing, the reason Allen variance is so important in this area is that if you just watch, the error when a frequency source shows up. So you got a rising edge, and then later another rising edge shows up with a little error. And then later another rising edge shows up with a little bit more error. That error increases that balance. So it gets a little difficult to figure out how erroneous your given oscillator is. What David Allen figured out in 1966 is that the difference between individual periods, that converges. So that's the magic number that we use in order to compare performance, because that's something where the more data you take, the more accurate an estimate you're getting, as opposed to if you're just looking at jitter, the more data you take, the more error you're going to accumulate. You're just like, I don't know when to stop. It's just getting worse and worse forever. All right, so that's Allen variance. If we use a temperature-controlled crystal oscillator, so this is kind of the gold standard for you to really high-quality crystal. I've got this Allen deviation plot. I've got this magic 20 ppm line drawn here. You draw this line across, and no matter when in time, every microsecond, if you're talking about data rate, every 1 second, if you're talking about sleep time, no matter how long you wait, you're below this 20 ppm error. Everything's good. This is what you expect. This is why you use the crystal in a commercial wireless communication device, because it's always going to be below the spec. That's not a coincidence. The specifications are written assuming that you're using a crystal, and so that's your major constraint. That's your source of time. I've got this inset box about the real BLE carrier drift specification because I have kind of a bone to pick with Bluetooth Stick about this. If you read the BLE spec literally, you need 0.17 ppm error, which is not going to fly even for a high quality crystal. If you look at the error over the length of an entire packet, you need something like 21. Okay, great. That's much more doable with a temperature compensated crystal. There is a commercial company called Aeroflex that makes test equipment, and how they test Bluetooth carrier drift is they look at 50 microseconds. They pair it up. They go, okay, every 50 microseconds, how far we drifted. It's not quite what the specification literally says. Fortunately, the proof is in the pudding. We plug this in and we transfer the chip and our phones can hear it. So there's at least some demonstration that we can do to show that we're meeting spec, at least as understood by other device manufacturers. But figuring out whether everything works in theory compared to the application, that has been a little fun. So the bottom plot here is just the same one as before with all the extreme stuff coming. One of the first things we designed was a CP clock. We want to run it at 20 megahertz. It only burns 1.5 microwatts, great. But if we type this out to a frequency counter and we look at how erroneous it is on an Allen deviation plot, it's terrible. And that's fine. A digital system just needs a rising edge eventually. The time between each rising edge doesn't really matter. As long as that rising edge propagates through the digital fabric in a synchronous way, you don't end up with horrendous race conditions or something like that. As long as that propagation path looks good, the clock tree looks good, when the next rising edge comes, you don't really care. And you certainly would not be using this thing for RF communication. Unfortunately, it would be nice if we were pleasantly surprised by this measurement, but it's way too erroneous in order to face wireless communication. The big innovation, the big thing that we figured out 5 years ago was that an LC tank, on-chip inductor and capacitor, over time is below the 20 ppm. That was huge, right? What this means is that once we initially calibrate the thing to understand what 2.4 gigahertz means in the first place, and we have some optical methods of doing that, some RF methods of doing that, instead of using a phase locker on chip. Once you do that, the error, moment by moment, while you're doing communication, meets the spec. And so we've been able to demonstrate interoperability with 50.4 devices. As I said earlier, you can transfer Bluetooth packets from this thing, your phones can pick it up, all in large part because this plot is below this 20 dBm. And as I mentioned earlier, we redesigned this whole thing in 28 nanometer in what I call tape-out class a long time ago. That class is now continuing. We had 10 students at the beginning. I think the most recent one they did last month had 75. They've gone from 28 nanometer ST Micro. They just designed, instead of one chip for the class, 2 chips. They split the class into halves. They had 2 teams, both designing an Intel's 16 nanometer FinFET process. They did some just incredible things with this. And you can imagine if you redesign this same basic digital layout in something even more aggressive, like 5 nanometer, this chip is going to become vanishingly small, except for the 5 icons I've outlined here. Right? Faraday's law doesn't care about Moore's law. You're just going to have, eventually, at the limit, you're just going to have a big spiral inductor, 2 big spiral inductors that's in the entire chip. So one of the other things that our lab is pursuing is, what if you eliminate that thing instead of an LC tank oscillator? You switch to a ring oscillator. They're much noisier. They're a lot smaller and lower power. We're not quite there with standards compatible communication, but I have 2 new PhD students starting this summer, and I have some ideas, and by God, we're going to figure this out. Don't quote me on that. Okay. So where I see this scaling to is going from, right, PCB, eliminate the PCB. Okay, now we're redesigning it in 65 nanometer. Right, we have this research project in TSMC 65. This is all the scale up here at the top. We go from something that's a centimeter on the side to something that's a couple of millimeters on the side to something that's just over 1 millimeter on the side. Hopefully here we can have something that is teeny dots that you can barely see, all approaching the Larson localizer from Werner Benji's deepness in the sky. That's the goal there. That's my guiding line. What can we do with it in a hurry in the last couple of minutes? I think I've got 10 slides here, so it's going to be a little rapid fire. Well, we know air quality tends to go heavily in summers, and we know that if the particle counter map I've got here is any indication, most of the state has no idea what their air quality is like. And we potentially change that. Well, a couple of years ago, we demonstrated that we can attach a harmful gas sensor. In this case, it was hydrogen sulfide. The sensitive layer, if you really squint, the actual sensitive point are these 6 gray bars here. That's the chemical sensor. So you can coat this thing in a variety of harmful gas sensing surfaces, attach all of those to this analog front end, digitize it, transmit it out, have that be part of a multi-hop mesh network that gets all that data. Eventually, there's going to be a bit of latency, but when you're talking about gas in the air, maybe even a couple of minutes is probably acceptable. So you can scale this up and just have zillions of harmful gas sensors on here. And eventually stack all this stuff up. At the bottom, you've got a battery, you've got the single chip modes communication device in the middle, maybe a solar cell. A solar cell at the end of the day is just a PN junction. You can have lots of those in CMOS. So why not just make the chip a bit bigger with a bunch of areas that soaks up light? And then a bunch of gas sensors. My guess is to put 6 here just because I had a demonstrator on the previous slide that included 6, but lots of gases have been demonstrated. In this case, we wrap it in transparent epoxy with a little cap at the top so that you're exposing some of these sensors to air. Then you've got kind of a distribution problem. But you could really feasibly place these at 1 kilometer spacing across the entire state. I've run this grid at 1 density just to get you in the mindset of exactly how many devices that is. It's about 250,000. But our reasonable cost estimate here is something like 20 cents per node, about 5 cents per piece on 2 slides ago. So that's 50 grand. For a state budget, not too bad. We got to figure out how to put them out there. So my first thought is you have a drone with a BB gun. You just fly a kilometer, flies a kilometer, and then they light up, right, as soon as if they're oriented up, maybe you have to fire a couple of them, so that on the off chance they have face down, well, that's not gonna light up. Maybe they turn on, and you can totally change what we understand about air quality. Locally here on campus, at 1 meter spacing, that's about 200,000 nodes for 40 grand. That would be really cool. And that's something we can do with the wireless radios we have today. They will get 1 meter range, no problem. 1 kilometer on the previous side would require a redesign. We probably want to switch to something like 433 megahertz, get a little bit longer, bigger and better. If you don't want to distribute heterogeneously, homogenously rather, across the entire state, maybe you want heterogeneous clumps. You could piggyback on some of our colleagues' work. Again, over in France, they just demonstrated a 103 kilometer 10-hop link with the OpenWSN mesh networking system. These chips already speak the same wireless protocol, and so as long as they're within hearing range of one of these balloons or something similar, then they can all group together on one of these nodes and then have this long range hop. So you can have a bunch of clusters connected, lots of possibilities here. Little background on OpenWSN, the website, which is openwsn.org. It's imported to a zillion platforms. Here at the bottom is the interface layer, but the rest is just a standards compliant stack of network devices. So all of these, all the layers above the actual platform are universal across the hardware platform. And at the very end, you go, okay, how do I actually port the function that turns on the radio or turns off the radio? When you port it to a new platform, you've got to figure out how the stack reaches through and actually toggle switches. But besides that, the rest is pretty bulletproof and has been ratified by the API. Yeah. Long battery life. All right, that said. And my favorite example, personally, is that once we get below this magic 2.6 millimeter dimension, now it fits in a standard surgical endoscope. So we can go from something where we're stuck at 1 centimeter and now have something that can be implanted in the body using routine surgical tools. If we can fit a little battery in the same cylinder, that would be fantastic. I'm looking for partners who can design little printed rolled cells that are in the same outer diameter. But if the brain of the device is under 2.6 millimeters, now you can start doing some crazy healthcare stuff, which is really amazing stuff, in my opinion. So that's the long and short of being able to design entirely in silicon. We can make a complete module. We can do new science. We can create new instrument platforms. This is my little plug for the open source design tools, which I'm sure this audience is no stranger to. There are a couple talks this week and about these. When I sit here, I hope you saw my student Richard Adams talk. He came down with something, unfortunately, and had to, maybe he's only going to reschedule, maybe he'll end up giving a talk tomorrow or Sunday. But he originally had a kind of how do you get started in open source IC design today talk set up. So hopefully he'll be able to come back and give that talk. But Mohammed Qasim is one of the biggest players in the open source IC design world. And he's got a talk, and I got a second later this weekend. So if you're interested in IC design, the most accessible way to get started is the open source tools right now. That has completely changed the game. Just like moving from this kind of arcane microcontroller design world and then being able to just use Arduino and how to work and how to be much more accessible to people. The open source IC movement is doing the same thing. It used to be something that was very secretive. You kind of have to apprentice into learning how it works. It is really like horrendously complicated. It's still fairly complicated, but at least the tools are much more accessible. Anybody can just download them on their own PC in the middle of the night and get started on it, as opposed to needing to join a PhD program. So that's it. Now you take questions. Thanks, everybody. We'll start in the front.
So I didn't hear the words energy harvesting at all in your presentation.
Yes, that's true. Energy harvesting is it's a rabbit hole that I stay far away from as much as possible, just because if I can draw a kind of clean break and draw an interface at VDE, right? I assume we're gonna get 1.5 volts from somewhere, then I'm happy to kind of move forward from that and do more RF circuit design on the other side and partner with folks who can do the energy harvesting stuff. That is, it's an entirely different world from my specialty that I want to identify the interface and go, if you have energy harvesting ideas, please, let's plug them together. But you're absolutely right. Being able to harvest the energy is the key to very long-lived deployments across the state, across the world. Yeah.
Silicon Valley's oscillators are a thing these days.
Yes, they are.
They seem high power. Can you talk a little bit about why we haven't seen more of this LC stuff instead?
Silicon crystals as opposed to quartz crystals. Right? Companies like SiPion are absolutely destroying the field. Right? They have just incredibly high performance and actually comparable power consumption, even lower power consumption versus crystals. They're still an on-chip component, so that's versus quartz crystals. They're still an on-chip component. I'm still interested in eliminating them. The most compelling, the most sort of highly integrated product I've seen is Texas Instruments now has an integrated bulk acoustic wave resonator that provides a very highly accurate sense of time, all in one package. So that is really fantastic. It's still kind of a post-processing thing, but my suspicion is that the reason we don't see a whole lot of this compared to just go ahead and use a resonator of some kind is because they want customers to be able to plug it in and make it work. What we need to do is go through kind of a lengthy calibration process when we power the thing on. We're optically programming it, we're providing tiny pulses, it's finicky. And what companies like Texas Instruments are interested in enabling, I'm guessing, is much more out of the box. It works. The RF communication layers just work. They're robust against temperature, and they're not going to be fielding a whole lot of frustrating customer calls to say what is going on. In the academic world, we're happy to field it. I think there was a question. Yeah.
What's the current power usage on the SoC basically right now? What are you getting? And also from that, you mentioned the power harvesting, but are you able to do similar tricks with, say, how RFID is able to be powered by a remote reader? And so if it's picking a signal from the mesh network, can you get power from that?
Right. Yeah, that's a good question. So in terms of active power, in transmit or receive mode, it's about a milliwatt, ground numbers. That's one of the reasons why the slide I had to skip earlier, like the estimate that I have of scum with CR2032 battery at sort of iBeacon level communication, why I would estimate that we're going to get something like in excess of 10 years battery life there, except for this top bullet here, which is that our leakage current level is really high. There's just some set of gremlins in the chip right now that means that we try to power off all the nodes that we have, we still end up leaking our hardest time. It's something that I'm happy as an academic to sweep under the rug because it's been demonstrated so many times in industry. It's something that low power modes, sleep modes are kind of well understood. It's not an interesting research project. So, we present this at a conference, people go, yeah, but all these other companies already do this. If we end up with enough interested student work, basically, we can attach some more intelligent digital controller. That would be great. But the sleep current is kind of fun every time. We want to plug in a small battery, and battery's just going to die pretty quickly because of the sleep current. But the active current is sort of the differential that's consumed when we're turning on the transmitter or the receiver is still 85 times less than most commercial. And that's thanks to really innovative RF design work done by my colleagues back at Berkeley.
What methodology are you basically sleep node off of? How are you moving?
Right now, our sleep mode is just definitely a hack. It's limited to downclocking the CPU. Okay, so sleep mode
Really
versus,
just lower the.
yeah.
So like it goes from 20 to like what, 5?
From 20, it goes from 20 megahertz to 78 kilohertz.
Oh, okay.
Really put it in deep sleep. And it's a single, it's an atomic operation to switch the CPU clock back to full speed. Full speed. Yeah.
And what do you think how long of a time period you're saying this, not this research, but is this, 10 years worth of work, 10 years worth of work, months worth of work?
Great question. So one slide I had to cut through, and you're talking about this for 2 or 3 hours, was the wall of people who contributed to this. This was 3 PhD dissertations, 1 postdoc, about 20 master students who contributed, and maybe 30 undergrads, all over the course, starting, I started my PhD in 2012. So something like a decade times many people contributing design, unique designs that had to be painstakingly verified. And so we picked out, I think, 6 chips and finally got something that worked with the 5th one and made some improvements after that. Yeah, lots and lots of effort. Certainly something that you're not going to rapidly prototype terribly easily. But that's something that we also really want to change. We want to make this something where it's essentially hard IP. You drop in and synthesize around it, and now you've got a radio. Yeah.
Are you looking for collaborations with other universities or?
Yeah, absolutely. Collaborations with other universities, other institutions that can plug in complementary components and make this better than some of the parts. Absolutely. So more fantastically sci-fi sounding paper. I think, should I cut it off and take questions offline?
Sure.
Time?
Yeah, if you're ready.
Okay, so we'll cut things off there, but I'm happy to answer questions up here for at least the next couple of minutes. Thanks again.